Well, Peter, welcome. It's great to have you with us. I love hearing about folks' background and what brings them to doing the things they now find exciting. You went to Chicago as an undergraduate and did mathematics as your major, and then went off to CMU to do computer science. What provoked you to decide going from math to computer science?
Yeah, that's a good question. At University of Chicago, math was sort of a default path for me in some sense. I came in with I had been in an advanced program of mathematics in high school. I had the great fortune of being part of a program at the University of Buffalo that took students in high school through high school math and then fairly far into college level math while still in high school. And so in some sense I did the math major at Chicago mainly so I would have lots of time for electives.
I see.
In a whole bunch of other areas. But I was really I'd from an early time, and I think I actually may place it to a one of these sort of career day events where they brought us from our must have been high school or maybe it was even middle school to research labs at the university in Buffalo, and then introduced you to here's what happens in a chemistry lab, here's what happens in a biology lab, and was there sort of introduced to the idea of how amazing the things the human brain does just through a little exercise where they just told us on this piece of paper, identify the squares and the triangles and the circles, which is trivial for us, but was sort of at that time cutting edge computer vision, and just really drove home to me how far we were from being able to understand how the human brain works or to be able to replicate it. And so I sort of spent my college years at Chicago sort of trying to figure out what was the right field to get at that question of how does the brain work, how does intelligence work. So I went to a neuroscience course and learned how synapses worked and axons and dendrites and but nothing close to getting us towards intelligence. And then I went to some psychology classes where from the other end saying here's some behaviors, here's some theories on how they work, and then it was in the computer science classes, and there happened to be at Chicago at the time there were a bunch of faculty who were former students of Roger Schenck at Yale. So there was Chris Hammond and Jim Furby and Chris Owens, and I took a series of courses with them that really sort of inspired me to think about artificial intelligence, and that's where I sort of got was much more satisfied than in the neuroscience courses and the psychology courses, that we were really trying to get at it at the level that felt visceral to me, that I felt like there was progress on really theorizing about what is intelligence and then trying to build artifacts that would mimic that as a way of doing it. And so I asked them, where should I, if I want to continue studying artificial intelligence, where should I go? And they pointed me towards Carnegie Mellon, and then I was off to the races.
That's interesting, and this was a great time. My sense is for when you actually went out to CMU to do this work, it was kind of the blossoming of an acceptance of probability theory and uncertainty, action under uncertainty. These were the kinds of things that I and my colleagues had to fight for as grad students a few years before when we were at Stanford. And working with other folks and other grad students in my cohort at CMU and MIT, we had kind of the rising college of folks interested in uncertainty. Mm-hmm. But you came into that world, and did you right away head into robotics?
Not right away. So my first year, I was working in classical planning in the Prodigy system. That was Jaime Carbonell and his students, and then my advisor Manuela Veloso. She did her PhD thesis in the Prodigy architecture. So I started off in classical planning for the first year, and some of my first papers were published in that area. But it was after my first year of graduate school, I went to the AAAI conference. It was actually here in Seattle.
I remember UAI and AAAI that year were in Seattle. It was a fun summer.
Yeah, and so one of the demonstrations, they had demonstration rooms, and so there was a room with a demonstration. It was by Alan Mackworth and one of his students, Michael Sahota from University of British Columbia, and it was a robot soccer demonstration. But it was, it had a ping pong ball on a ping pong table, one robot on each team, sort of, moving around. And they had some research. They called it reactive deliberation. So it was sort of bridging the gap between sort of the robotics theory of the day from Rod Brooks and on subsumption architecture and everything being straight from sensor to action, reactivity to to the more classical planning, trying to deliberate, decide what to do. But I had been, at the time, I was and I still am, I was a soccer player. I played on my college varsity team. I looked at that and I thought, well, that looks really inspiring, but it's not really soccer. There's only one robot on each team. That's team. It's just one-on-one. And so, and then I thought, well, and it actually has connections to what I've been working on, planning, but now within a dynamic world, and there's, could be multiple agents on each team. It could really take planning to the next level. And this is a story that I like to tell of, I was really good friends, and still am good friends with Astro Teller, who's currently head of X. We were both advisees of Manuel Veloso. Yes, that's right.
I said X very quickly, so make sure people hear that, yeah.
But so Astro and I were co-advisees of Manuel, great friends, and so I told, and we also played soccer together. So I was telling him,
So Astro was in school with you at the time.
Yeah, we entered Carnegie Mellon the same year. We shared an office all the way through grad school, and so and we played on the same soccer team, and so I looked at that and said, oh, that would be a great area to do research on. And so we spent like a couple days bouncing ideas off each other. How are we going to convince Manuela to let me do research, for my PhD on robot soccer? And so we came up with all these arguments. Oh, it's related to planning.
And this was for you or for both of you?
For just me.
Oh, okay.
Astro already had his plan. This was just for me.
Okay.
So we had it all down, and I was ready to go in and just lay it all out. Here's how I'm going to convince you that this is a great domain for AI. And then the next time we saw Manuela, she was coming down the big escalator in the convention center or in the hotel or wherever the conference was. We were going up, and Astro just shouted, "Hey, Manuela, Peter wants to work on robot soccer." And Manuela said, "Oh, okay." And
then the escalator just passed in the afternoon. That was it.
And so that was, after my first year, I then went back and we decided I started with the simulator that Alan and Michael had used at University of British Columbia. And then we also said, let's actually build our own physical robots. I didn't know anything about robotics at the time, but we brought in a mechanical engineer who built some robots out of basically a glue gun and wires. He just got some wheels and wired these up. He was definitely not an electrical engineer. He was a mechanical engineer. So, but we got them so that they could move, and we got a camera, and I started looking at vision algorithms and all sort of trying to get this working from the perspective of this is a great challenge that would unify planning, which is where we were coming from, but also expand towards robotics, multi-agent systems, and reasoning under uncertainty became a really big part of that. And so, machine learning, how would you get these agents or these robots to improve over time? They have to take actions. How do you take actions? That's through reinforcement learning, and reinforcement learning is built on reasoning about uncertainty. And so very quickly, it was just sort of natural to me that this is the way we would go in the research. And it was, I think, like you say, it was a time people had already embraced Bayesian reasoning for some aspects, but I think reinforcement learning was still, learning about how to act was still a very nascent area, and that was the fringe. That was, you'd go to the machine learning conferences, and there'd be like 2 or 3 reinforcement learning papers, or maybe one session, and most people thought of it as sort of the crazies. Who you'd have to convince people to work on reinforcement learning.
And to be honest, the theoretical principles around reinforcement learning was still evolving at that time.
Well, it was the probably the landmark that sort of launched reinforcement learning into the sort of modern era was the convergence proof of Q learning, Watkins' thesis in '89, and I started my PhD work in '93. So it was still young.
There, yeah.
It was around, but it was young, and now people were really trying to build from that, but in very sort of small, theoretically grounded settings. They weren't really embracing the big problems of trying to make this work in practice. And then, not long after, I guess, a big sort of focal point for the community was when Jerry Tesaro at IBM did NeuroGammon, did learning backgammon using Q-learning, and so that was sort of a demonstration that, look, you can do this on more than just grid worlds, and but still most of the community was, and to some extent still remains, very theoretically oriented, which sort of tied them to smaller problems. And I always wanted to say, how can we just, even if it's not theoretically guaranteed to work, could we use this in a multi-agent setting or in a robotics setting? And so that's where my focus was.
So Peter, what's your sense of this interesting, it's not exactly a trade-off, but maybe a choice about understanding and pursuing deeply, but in a narrow way, technical extensions where you could really more easily plot your course theoretically to extend the theory, versus taking some understandings and jumping into bigger problem domains where you might have trouble wrapping one's mind and one's theory around the big problems. I do imagine these could frame lots of interesting new questions, but what is your sense about, when to do what?
Yeah, that's a great question. I think about that a lot. I think there's a really important role for both types of approaches. And in fact, I insist on PhD students in my lab. I've had students, and I have students whose natural tendency is to start from first principles and to start from algorithms and build off and take that next theoretical step. For those students, I insist that, okay, let's do let's prove what your new algorithm, your new theorem is, or what the new algorithm is. Let's develop it. But you're not done until you apply that to something. Let's show us what it's good for. Try to bridge that gap to understanding, how far can it get you. And then I have students who really, they're more engineers at heart, and they say, I want to start with a problem. I want to solve that problem.
By hook or by crook.
By hook or by crook. And I tell them, look, you can solve that problem, but you're not done until you can now distill away what is that key algorithmic contribution that you made and show, what's that nugget that could apply somewhere else as well, right? That's not just for your problem. And so I think, traditionally, when AI started as a field, there was no option. You had to sort of start from the bottom up and work on the basic principles. I feel lucky that when I came into the field, there were enough tools in the various different areas. There was rudimentary vision and natural language processing and planning and robotics that you could take a problem and say, let me take the best of the technology that's out there right now, integrate, put them all together, and figure out where they're lacking. And where they're lacking is going to be what motivates the research, the research that I'm going to do. So I said, I'm going to try to solve the robot soccer problem. Okay, we're pretty good at navigation, but the vision is passable, but we still don't know what how to make the decision. So let's try to work on reinforcement learning for that. So it's more like, I think I would never advocate that everybody should work in one mode or the other. I think there's great productive room for productivity in either realm. I think traditionally in the field, the sort of more applications-oriented research has been underrepresented, and so I feel it's been part of my role to try to evangelize that a little bit, that it needs to be appreciated, that the challenges of integration, it's not just putting pieces together, there's actually research in how do you put those pieces together and what problems can we do now and what do we still need, what pieces are still missing, and then trying to make progress on that. But it would be a horrible state of affairs if everybody started doing that and nobody started trying to, kept at the basic algorithm. So I think it takes all types, and that's what's exciting about the community, and I try to make my lab as much as possible bridge that gap, and make sure that every student who comes out has sort of wherever they started, they at least take a step in the other direction.
Right. I think it's interesting to think, just to look back on problems I've worked on, this idea of starting big sometimes in new areas defines new interesting directions that become interesting pieces of theory. If you recall any particular examples of that.
Yeah, in my own research, when I came to try to do decision-making reinforcement learning for for robot soccer decision making. There was no really multi-agent theory of reinforcement learning and so I had to introduce a new algorithm as part of my PhD thesis for multi-agent reinforcement learning that sort of I think it wasn't beyond what people could conceive of, but there were still so many other problems that people were working on. Nobody had gotten there yet, and it was an immediate need for me, and so it's sort of absolutely. I think there's lots of examples of that. When I've some of my work in the trading agent competition, there we needed to develop I was working with Rob Shapiri and Michael Kearns and Satinder Singh, Michael Littman back at AT&T. And there was a particular decision-making problem that we needed to address, that was because of the rules of that competition that basically inspired a new extension of a boosting-based algorithm for logistic regression that was very tied to some of the research that Rob Shapiri in particular had been doing at the time with Joachim Freund, but was a new extension that I think never would have thought to go down if we hadn't had that need from the actual domain we were looking in. I think it happens all the time.
You mentioned the work in trading. So how did you get in some ways people might say, okay, these are all agents and decisions under uncertainty, but the trading world is very different in some ways, or I should say many ways, than the teamwork agent space for robot soccer. So what's the link there in your mind?
Yeah, so this was at a time I had finished my PhD. I was now at AT&T Labs. I was getting people there involved. We had a dream team of people in reinforcement learning there. It was a really phenomenal environment. And I got them involved in some of the challenges on robot soccer, but I was also looking for some new direction to go in. And I wanted it still to have to do with multi-agency and machine learning. And it so happened that Mike Wellman at the University of Michigan and his group were thinking of trying to build a competition for trading agents that was inspired by RoboCup. And so I had a conversation with him. He was
I didn't even know that.
Yeah.
So this was like the trading variant of RoboCup.
Yeah, very much so. I don't know how they originally conceived of it, but certainly he asked me as one of the early participants in RoboCup for my experiences on what are the pros and cons of running a competition. What are some of the pitfalls they should avoid? And so I consulted with them and worked with them on this domain, and it intrigued me because it did have many of the same properties. And in fact, I have an early paper after having spent a year or two doing the trading agent competition, sort of comparing and contrasting robot soccer and trading agents as domains for artificial intelligence, as competitions, as sort of multi-agent environments. And yeah, so to me there's a lot of connections, but it is decision making, reasoning under uncertainty and uncertain futures. Some of the same kinds of techniques and methods apply, but it was also a way of branching out a little bit and not just working on what I had always done in my thesis.
Now I recall that you were one of the most energetic of the folks involved in this Asilomar study AAAI did that I put together with Bart Selman and others back in 2008, 2009. And this was all about thinking about what we were calling then, which resonated deeply with you, I would imagine, AI in the open world and long-term AI futures. Early on, you were one of the folks that had sort of deep interest and passion in the implications of these technologies as they evolved for people in society. I'm not sure if you have any comments about that in terms of your involvement in that space and why that was so important to you.
Yeah, no, I do. I mean, it's to me, we're dealing and creating a very powerful technology, potentially very powerful technology, and that has the potential, and we're seeing very much so in these days, to really shape and influence and change society. And coming from a liberal arts background, and I'm not a pure technologist. I don't think that we should. I think it's not just let's do what we do things because we can. We should also be thinking about the implications. And yeah, the Asilomar meeting was one of, I think, may have been one of my first sort of experiences with people really thinking about this and putting verbalizing it. It had been sort of percolating in my mind a lot, but I really valued that you put that together, and it's led to we've worked together, and I was very honored to be the first study panel chair for the AI 100 study, where we really jumping ahead several years then, I guess almost not quite a decade later. But and that now has actually led to a much bigger effort at the University of Texas at Austin called Good Systems, a grand challenge project that's really brought together engineers and technologists with people from the social sciences, public policy, law, thinking about what actually does it mean for a technological system to be good. How do you build a good system? But first of all, what does it mean to be good? How do you, evaluate whether something is good? And then how do you build something that's good? And I'm on the organizing committee of this, and it very explicitly did come out of the sort of the study panel report of the AI 100. And one of the ways I like actually thinking about this now is that there's sort of two axes of you can add many more, but the two axes I like to think about of technology are along one axis, how beneficial it is for society, and on the other axis, how easy it is for society to accept it. And I've actually, as you know, I've done research in self-driving cars on autonomous intersection management and things like that. I'm quite convinced that if we could get to a point very certainly if all the cars on the road were autonomous, but probably even without that, we can get to a point where there are fewer fatalities if cars were autonomous. Yet it's really not clear if we're ever how long it'll take for people to accept them. Regardless of how good they would be, there's this sort of acceptability barrier. And so, you have things that's just, a potential example of something that could be very good but difficult for people to accept. And then there's other things like social media that people are very quick to accept, but it's very debatable whether they're good for society. And really, what I want, and what, as a technologist is to think about how can we build things that are both good and can be accepted.
By accepted, you mean by socially acceptable, psychologically? Do you mean costly to accept?
So all of these things, right? So it's not just whether something is technologically possible. We have to have the social acceptance. We have to have it be cost effective. There has to be the legal framework around it, possibly the insurance framework around it. There's lots of factors that go into determining whether something that could have a lot of beneficial impact actually will. And so, and that's, for a system to be good, it has to actually have an impact, right? It's not just, you don't want to just leave it as potential. I've always felt it is a responsibility, especially in AI. It's so, people come to AI with, sort of impressions from science fiction often, and so either the doomsday, dystopian view of AI, or the more optimistic utopian view, but very rarely the middle road, which I think I've always felt is the case, that there's potential for AI to do good, there's potential for AI to do harm, but it's not going to just happen. We have to be thinking about how to make this, these worlds come about. And so for many years I've given in my talks, I've asked, in my especially outreach talks, I've asked people to engage in discussion about just the general trends of technology. Is technology making the world a better place, or is technology making the world a worse place? And so the way I ask that question often is I say, if you had a choice of being born either 100 years later than you were born or 100 years earlier than you were born, which would you choose? Now, in a room full of...
Can I get a Geiger counter reading?
Yeah, so that's one of the questions, right? There's a leap of faith to going ahead 100 years. Will the world still exist? Will there have been a nuclear disaster? And in a room of computer scientists, still, even with that, almost everybody says, I'd like to jump forward. But if you
Yeah.
engage in this conversation with people from across a university and talk with people in the social sciences, and you'll get some pretty impassioned and arguments that, first of all, there's a lot of uncertainty in it is a leap of faith that, the world may not exist 100 years later from when you were born. But also, some very real senses in which, they feel like the technology is decreasing quality of life. And I think it's important as people who are causing these changes to grapple with these issues and to have answers for them. And if you think, I wouldn't be doing what I'm doing if I didn't believe that technology, and AI technology in particular, is making the world a better place. But it's not a given. Just because we can do things doesn't mean we should.
And of course, there are different hands these technologies can fall in, and different uses that might come of their desires and goals of the owners of the technology someday. If you think back to, again, your own career, your mentoring of many fabulous students over the years, several we met today at Microsoft Research and at Microsoft Corp. What kind of advice do you have to, let's say, somebody who's middle of undergraduate years, getting excited about maybe engineering, mathematics, or even liberal arts more generally, about how to choose a career, how to navigate per one's interests and one's sense for things?
Yeah, I mean, it's a great question. People get asked that all the time. I happen to have children at about that age, so I give this advice. Does not always get listened to, of course. But I think number one, I mean, it's cliche, but follow your passion. You're going to be spending a lot of time working on on what you're working on, whether you do a PhD, whether it's your career. A large fraction of the hours of our lifetime are spent at work, and so the most important thing is to work on something you enjoy doing, that you care about. In terms of I actually think like as we talked about earlier, I think when I was an undergrad, it was too early to get into neuroscience. I think there was the level of understanding was at a level far below what I wanted to be able to study intelligence. I think there's just from the perspective of what drives me into getting into AI, I think there's a lot of exciting developments coming down the road in neuroscience, computational neuroscience, and so for somebody with that kind of inclination, I'd say give that a shot. I used to say that when I took my first neurosciences courses, I'd say if we ever got to the point where somebody could tell me physically what changes in my brain when somebody tells me their phone number and I remember it, like what are what's the mechanism, that then I would drop AI and move to neuroscience. And I think nobody's been able to tell me that yet.
Now you sort of know the secret reason why I have this mysterious MD degree next
Yes.
to my title, my PhD.
Yeah, no,
I'll say we're gonna go back, put my lab coat on, and
Exactly.
get into the neurobiology.
No, I think it's a great. I mean, the time is getting closer and closer. I think there's a lot of we're getting and it's exciting to see people, young researchers coming out who have a foot in computer science and in neuroscience and are sort of starting to bridge that gap. So that that's one thing. The other advice I think is really sage for young people coming up is to be an expert in one thing. There's always going to be a lot of people. But if you can be an expert in two things and merge them, so like you said, having an MD next to your name and the secret one, but
that's there for that moment when I go back to the lab.
Yeah, but I mean, even so, I think having being able to bridge disciplines is, I think, very valuable and is less. It's always going to be a less crowded area than being an expert in one thing. So being able to have a grounding for me, my degree was in mathematics and I ended up in computer science. I started off in planning, but then moved to robotics, and having these sort of expertise in multiple areas.
Very interesting.
In any one area, you're sort of trying to make a name for yourself in a crowd. But when you're the person in that area who has an expertise from that other area, there's much more space. and room to grow and contribute and make a name for yourself, as long as that's compatible with what your passions are. I think that there's a lot of potential benefit for a young person to be able to think about what's the new perspective they can bring to the area that they're most interested in.
Given everything that you've been looking at, studying against the background persistent question about what's going on with the human brain, do you feel like you, and this is the cocktail hour part of our discussion, do you feel like you have any new intuitions, or is it still a complete mystery about how on earth these tangles of neurons do their thing to give us these abilities and this sense of even being?
Yeah, I'm not going to claim to
No,
be able. I've done some fascinating collaborative research with neuroscientists and worked, in fact. One of my former students who's now here at Microsoft, Matthew House-Connect, and I did some joint work with a professor in the neuroscience department, Mike Mock, who has a wonderful simulator of the cerebellum and is one of the world's experts on how the cerebellum works, which is the part of the brain that does the kinds of things that reinforcement learning algorithms do, sort of does some fine motor control kinds of things. So we did some great collaborative research with him. But really, he was the neuroscience expert, and I'm fascinated by neuroscience, but I can't claim to be making my own contributions there.
Let me ask you maybe something a little bit nearer in than just having you try to field the question about what's going on in the human brain. But speaking of neurons and nets of neurons, getting into the computational invariant of what we call neural net models, we've seen the rise and fall and the rise again, the renaissance of these methods. And it was great to see how you're using some of these methods like adversarial approaches to, in reinforcement learning and learning by watching kinds of scenarios. I'm curious what your sense is for how these technologies are now fitting in to the maybe earlier planning research, call it classical planning and agents research.
Yeah, so I've always taken a very sort of big tent view of AI. And in fact, I did start my first year as a graduate student. I was working in classical planning, but then when I moved to robot soccer, the first learning algorithm I used was a neural network, and I used decision trees, and I used reinforcement learning.
Which neural net were you using then?
I programmed my own. I
see.
think, I think I first tried programming my own, and then I think I used a package from Andrew Moore's lab that they had built, but for themselves. So, but it was for a specific subproblem of robot soccer, was trying to get an agent to figure out where it should move to try to intercept a ball. And actually, as my undergraduate research project at University of Chicago was in the applied math department on implementing a neural network. So I've actually been a fan of neural networks from the beginning, but not as the exclusive role. And kudos to the folks who've really been pushing that approach, even when there were people who were poo-pooing it and saying, oh, that's not going to get us anywhere. I've always been sort of hopeful that they would be of practical use, and like I say, I've used them. I think the pendulum may be swinging too far, though, in the sense that the stories that these people tell are that, oh, isn't it great that while the whole rest of the field was working on other stuff, we kept the torch alive and kept neural networks going, and now they work, and so everybody should do neural networks, and we shouldn't keep any other torch alive. And I think that's going way too far. I think neural networks are fabulous. There's been some great, really surprising results and capabilities from them, but they're not going to do everything. I don't think this is debatable, and people will debate me on this, but I think we're a far cry, at least, from them being able to solve the entire intelligence problem. I think they're a very important tool in the toolbox. But I think for the kinds of problems I'm interested in, at least in the foreseeable future, we're going to need to bring to bear lots of different AI tools from the toolbox, and that includes symbolic and classical reasoning, and that there's a nice thriving community that, in some sense, is now the analog of the the neural network community that's sort of struggling to keep a voice and be appreciated. I think there'll be that day in the sun again for this community, and of course probabilistic reasoning and Bayesian reasoning I think is something that that these are never going to go away. I think what we need to be doing is understanding more about the strengths and limitations of each of these approaches and how to put them together into functioning systems. And I think it's great that there are some people who want to push neural networks as far as they possibly can go and try to understand what can we do with end-to-end neural networks. But I resist if the claim starts being, and that's the only thing the entire community should be doing, because I think that's going way too far. I think we need to, like I say, the big tent view of AI, I think there's room for lots of different approaches and to understand what the strengths and limitations of all of them are.
So Peter, you said that by the year 2050,
that we can build a team of humanoid robots that can beat the best World Cup champion at soccer on a real soccer field.
Okay, so
I should say this was originally, I'm not saying it's not a prediction, it's a goal.
It's an aspiration.
It was an aspiration, and it was originally put out there by Hiroaki Kitano.
Okay, so Hiroaki Kitano, a good friend of both of ours, put that challenge out there. What do you think of that aspiration?
I think it's a fantastic aspiration, a fantastic motivating goal. When I sometimes put it in sort of context with, and I'm comfortable saying it in the same breath as a challenge of landing a man on the moon, the Apollo mission, and the challenge of sequencing the whole human genome, both of which have achieved their goals, that were sort of big scientific efforts that especially landing a man on the moon was not necessarily in and of itself of practical importance, but to get there, it was going to have to drive technology and engineering in new directions. And I see that's this robot soccer challenge is serving that role. It's a very easy to state ambition. It's very inspiring to people worldwide. It drives a lot of different needs from an AI and robotics and technological development perspective, and it really takes to the next level things like chess and Go and Jeopardy, which are where, and poker, where there's in some cases complete information, some cases incomplete information, but are not about physical interaction in the world as much as about pure AI knowledge kinds of systems. This we often at the time when Kitano put this out, it was in 1996 or 1997. It was right around the time of Deep Blue and Garry Kasparov and Deep Blue winning that match. And so we say, what are the differences between soccer and chess? Chess, you have discrete. You can represent the state as being discrete. In soccer, it's continuous. You have full information versus partial information because you only see in one direction, and you have a single
probability of success by then.
I really
just go for it.
I can't. I can be convinced either way. I can't. I don't want to be pinned down to a number here. I think it's the intelligence side of it I can get a handle around. The physical aspect of can you build robots that are as agile as people, that is much more difficult for me to imagine. But when I look back 20 years to the compared to the robots that are possible these days, there's been huge advances. So I wouldn't bet on it, and I wouldn't bet against it.
Well, that's a fine answer. I don't want to push you too hard on that. So what are the key challenges we need to solve between now and when that does happen?
Yeah, I think there's generally just there's two classes of challenges. There's the physical hardware. Can you get a robot that can run and change directions and manipulate a ball and then there's the cognition, the sort of the sense, decide, and act aspect of autonomous agents, and and then they have to come together, right? What kind of sense, decide, and act depends on how the hardware is going. I mean, it always has to be integrated, but there's challenges. I mean, in all of these aspects, there's still perception still has to get better. I mean, perception is great these days. There's been huge advances, but still. Not at the level of human perception and awareness of just put a robot on a outdoor field with people moving around at full speed and the ball. Like you're still from that egocentric view. It's not going to still not at the level of people. Certainly the actuation. There's still challenges on teamwork. I mean, really, there's so many different pieces that have to come together. That's what makes it fascinating.
Have you had a chance, in that you did so much great work on teamwork, going from single agents to multi-agents and then teams, to think more about what makes good teams in life with other humans, for example?
Yeah, and at first, I sort of kept to just autonomous agents and said, people are a pain. People are difficult to work with, and very unpredictable. But now we're moving into social robots and social robotics and service robots, and that the goal there is to just have your robots become a part of society, part of the fabric of a building, and that they can do the things that not to be indistinguishable from people, but to be compatible with people, and that's a very that's a teamwork kind of endeavor. And so one of the topics I've worked on and introduced in multi-agent systems is what we call ad hoc teamwork, the ability of an agent to be able to work with teammates it's never worked with before. At first, I thought of that as just all robot teammates, but really, to be a good team player means also being able to deal with human teammates. And so, we're thinking a lot now about how do you predict what people are going to do and respond appropriately. How do you actually influence how people are going to interact with you as an agent, as a robot? And so an example that we just published in Roman in one of the conferences on human robot interaction. It turns out that if a robot's coming down the hall towards a person, people in North America will typically move to the right. That's what they expect the robot to do as well. And we wanted to see, could we do something to get people to move to the left? And so our initial hypothesis was that we would just flash a blinker, and that people on the left, and people would interpret that as a turn signal, and that they would go to the left. Turns out half the people did, but the other half thought of it as a directional signal, saying that's where you should go. And so that didn't work. But then we took the next step of doing an active demonstration, of having the robot come down the hall, and when it sees the person, put on its right blinker and move to the right, to teach the person in one shot that that's what the blinker means. And then, almost without fail, when it got to the person and turned on the left blinker, the person knew what it meant and would go to the left. And so this is part of being a teammate, is being able to reason about what information do I need to communicate to this compatriot, to this teammate, and how do I do it so that I'll be able to not only predict what they'll do, but influence what they'll do. And I think that there's really fascinating research to be done in that space.
And for all we know, there's a gold mine of research that's already been done about people working together and collaborating. It's interesting.
Yeah, actually, one of my, I should say, I've had the great honor of on my thesis committee as a PhD student. Herb Simon was one of the members. And I would go into his office, and he has a great body of research on organizational theory. And so he always wanted to bring in the connections of multi-agent systems to organizational theory in businesses, and thought and helped me really think, even back then in the 90s, of how this emerging field of multi-agent systems was connected to this area of human organizations and teamwork. So yeah, it's always been there, sort of thanks to him, in the back of my mind.
It's fascinating. What a great opportunity to have worked with him directly. I view Herb Simon as a meta mentor, in that I would see him at meetings and conferences, and through mentors meet him and talk. And great to have had him on your thesis committee.
Yeah, he was
fabulous,
fantastic, and he was just a huge inspiration to all of us around Carnegie Mellon at the time. I was unfortunate to have arrived just a year or two after Alan Newell passed away. And I heard great things about him, and he was also, his influence lived on and was a big part of the culture at Carnegie Mellon. But I was very fortunate that Herb was still around, and to be able to just go into his office and talk about research. He was just always we'd always come up with fascinating new ideas. He was fantastic.
He also had a great set of heuristics. I remember a bunch of them. He would just tell me these mottos, like we would be talking about something, and he would say, "You really should go home tonight and write that up tonight." Mm-hmm. The idea of just getting it done now.
Yeah.
I love that. We can all use a little bit of that.
Yeah.
Can you say just a few words about what it took to stand up RoboCup?
Yeah, and that's a great question. I first of all, I should say I was I was a fortunate graduate student at the time that RoboCup got started, and I was one of the first people doing research on it in outside of Japan. But really, the vision and credit for it goes to I mentioned already Hiroaki Kitano and Minoru Asada and Itsuki Noda and the other folks in Japan. Also, my advisor Manuela Veloso got involved through the research I was doing with her and became a really influential part of the growing the organization.
How does it work? People that don't know how it works.
So
the competitions.
Yeah, so RoboCup it's actually a very interesting, fascinating organization by itself, and I just became president of it. There is a board of trustees that sort of like you imagine what they do dealing with where the next competition will be and some of the financial aspects, but then there's also it's divided into different leagues, each of which has different characteristics. So within the robot soccer realm, there's a standard platform league, for example, where everybody has exactly the same robots, but then they have to program them differently. And then there's a wheeled league where people have to build the robots, but they can have wheels and move around with a golf ball, or then a bigger size league where they use a real soccer ball. Then there's a humanoid league where you build your own robots, but they have to have two legs. And then there's other leagues for disaster rescue and RoboCup at Home and RoboCup Junior. Each of these has representatives on an executive committee that sort of ties all of them together to make sure that we're sort of pushing the scientific directions agenda in the right direction. Each of the leagues has a technical committee that decides on sort of what will be the roadmap for the rules over the next 10 years or so. An organizing committee that runs the competition for that particular year. And then there's one international event where everybody comes together every year, but then there's also regional events that people that have people who are don't want to travel or you can't take everybody to the international event. So you have there's a China Open and an Iran Open and a European Open and a U.S. Open it's just a really thriving, beautiful community of people, scientists, who are unified by sort of grand challenge goals, research objectives, with this sort of forcing event, or sort of focusing event of we have to make everything work by this deadline every year. And then we can go away and then think about the next advance that's inspired by what the others did. But it's a really thriving and beautiful community that really you can only get a real deep appreciation for it by coming and experiencing the competition firsthand. So actually, one of the things I first did as president was institute several different policies to try to bring people who haven't been to RoboCup. So I don't know when you were last at RoboCup, but you should really come and see it if you haven't recently. But it's yeah, I mean it's the events themselves are just full of energy.
How many folks come?
Usually 2,000 to 3,000 that are in the participants across the different leagues and including RoboCup Junior.
And are there just spectators too?
Spectators do come depending on where it was. The biggest was when it was in Japan. We did it in the big baseball stadium one year, and there were like people snaked around the entire stadium trying to get in the bleachers. More typically, it's open to spectators, but it's a science event. We don't make it an entertainment event. There's been some very, I think, important decisions that have been made. One is that it's not primarily a spectator sport. It's primarily a scientific initiative. Fantastic to bring school groups through and teach them about science, but it's not curated in a way that would make for a good TV show or that's just not been the focus of the community. And another really important decision, in my opinion, has been it's not about prize money, right? So you get these competitions like the Urban Challenge and things like that, where it's about you'll win several $1 million if you're the one who wins the competition. There's no prize money in RoboCup. The goal is or the benefit of winning the competition is basically the ability to disseminate what you've done to inspire other people. It's much more what academia is all about. And so you get people winning and releasing their source code and writing papers about it and sharing, and then people building on it the next year and improving as a community. And I think that's been a really important aspect of it.
So Peter, I'm going to make a commitment to check back with you personally in 2050. I'll give it till December
Okay.
31st to see where we are with RoboCup and the humanoid robots, but more about our understanding of the brain and AI more generally. So thanks very much for being here today.
My pleasure. Thanks for inviting me.